This is a free CCNP Enterprise Advanced Routing lesson. This lesson is part 3 of the IPv4 and IPv6 addressing and routing fundamentals. Let's get started. In this third and last part, we will look at Cisco Express Forwarding, and then we will look at routing fundamentals, and then static routing for IPv4 and IPv6. If you haven't seen part 1 and part 2, I'll encourage you to look them up, as a lot of the information we will discuss in this video are related to those sections. So let's start with Cisco Express Forwarding. If a packet comes into a router and is destined to a different subnet, the router will reference its routing table. So that's the first step. And then once the next hop is established, the layer 2 frame has to be constructed. So that's your destination source and destination MAC address. And in the case of the destination MAC address, the ARP table has to be referenced. So if there are no entries in the ARP table cache, an ARP request has to be sent, received, and then the ARP table populated. And only then the layer 2 frame is constructed and the packet can be sent out. This process is not very efficient in this case. So Cisco has come up with a different way of doing things. So combining the routing table and the ARP table, Ceph table was created. And in a sense, instead of a router referencing the routing table and then the ARP table, it will simply reference the Ceph table. And this means that the data structure of the Ceph table can be referenced to forward packets. This process is a lot more efficient than having to reference the routing table and then the ARP table. A router will have two planes. It will have the control plane and the data plane. So your routing table will reside in the control plane, and out of the routing table, the Ceph forwarding information base is created. This is your FIB. And out of the layer 3 to layer 2 mapping, which is essentially your ARP cache, the Ceph adjacency table is created. The FIB and the adjacency table are the Ceph primary data structure. So this is essentially your Ceph table. The information in the FIB table is very similar to what you can see on the routing table. And the adjacency table has the information that are needed to forward the layer 2 frame. So it will have your egress interface and your next hop MAC address. Now let's look at the routing information sources. So you take any given router, you will have the IP routing table data structure and the IP routing table. These are two different things. If you're running a dynamic routing protocol, the router will receive the incoming routing information from an adjacent router. This information will be received in the IP routing table data structure. And only the best routes are installed in the IP routing table. Directly connected routes and static routes are also injected in the IP routing table. Redistributed routes are injected back to the IP routing table data structure. So your IP routing data structure will be fed by the incoming routing information, as well as any routes that are generating in the router itself. So this is the redistributed routes. And this information combined will then be sent forward to the next adjacent router. So that's your outgoing routing information. The source of routing information are mostly connected interfaces, static routes, and then comes your IGP, so that's your RIP, OSPF, and ERGRP, ISIS, for example. And in terms of external routing protocols, there's only one, and that's BGP. What happens when a router receives routing information from two different sources? So for example, this router is receiving information about 172.16.1.0/24 via an OSPF process, and equally is receiving the same information, all the information of the same subnet via ERGRP. So which one is the best and should be installed in the routing table? This process is straightforward. We already know that only the best route is installed in the routing table, but how does the router select which route or which source is the best? In this case, routers use the administrative distance, the AD. The lowest number is the preferred number, is the most trusted. So the connected interfaces R0. If a subnet is directly connected, that is the best way to forward the traffic. And then comes your static route as a next option, where the admin distance is 1. And then you have your ERGRP summary routes, and so forth. A given route that has an admin distance of 255 will never be used. Let's look at a concrete example. So here on router R1, I can see that I have a route for this subnet, or this host IP address, 3.3.3.3. I can see that it is a /32, so it is a host IP address. And this IP address is known via OSPF process 10, and the distance, the admin distance, is 110. The next step is I went in and I configured a static route. So remember, your static route has an admin distance of 1. When I run my show IP route for the same subnet, I can see that the preferred route is the static route. So it's no longer the route learned via OSPF, and simply because the distance is 1. So let's see, how can I keep a static route configured and still have OSPF as the preferred route or source of information. If I go back and configure my same static route, but change the admin distance from the default 1 and configure 122, which is higher than the OSPF 110 admin distance, running a show IP route shows that the route is back to being preferred via OSPF. So this is an example how you can manipulate the admin distance to prefer one route over the other. Now let's dive into the static routes, and specifically the IPv4 static routes. I have these 3 routers directly connected, R1, R2 and R3. The subnet between R1 and R2 is 10.1.1.0/24, where router 1 gigabit 00 has the .1 and router 2 gigabit 0/0 has the .2. On router 3, I have configured loopback 0, which is 3.3.3.3/32. On R1, I configure a static route for the loopback 0 on R3. As a next hop, I'm using R2 gigabit 00 IP address. So when I do a show IP route for 3.3.3.3, I can see that obviously the route is preferred via static, the distance is 1. And my next hop is 10.1.1.2, which is router R2 gigabit 00. So everything is exactly as I want it to be, and everything is as expected. On R1, I run a show IP ARP. And at this point, I'm not interested in the ARP entry for 3.3.3.3. I'm only interested in the ARP entry for 10.1.1.2. So this is the MAC address that R1 received from R2 when it did send an ARP request for 10.1.1.2. And at this point, with this information, R1 can safely forward the frame to R2, and then R2 will forward the frame to R3. Now let's change the configuration of my static route on R1. Instead of using a next hop IP address, I'm simply using an outbound interface. And in this case is R1 gigabit 00. So any packets essentially that are destined for 3.3.3.3 will be forwarded out of gigabit 0/0. This is also confirmed when I do my show IP route on 3.3.3.3. I can see that the next hop is directly connected via gigabit 00. I no longer see the 10.1.1.2. And I can see no issues with the ARP entries either. So these 2 different ways of configuring a static route leads to the same results, but the methods are different. They are slightly different. One of them is better than the other. One of them is less efficient than the other. Let's look at a different example to illustrate this. For example, if I were to configure an IP route for a larger subnet, 172.16.1.0, and it's a /24, using a next hop of 10.1.1.2. For any IP address within this subnet of 172.16.1.0, so it could be .3, .5, .6, they will all have the next hop of 10.1.1.2. So router R1 needs one MAC to IP mapping. That's one entry in the cache. However, if I specify an outbound interface instead of a next hop IP address, I will end up with several ARP entries. So for example, if I'm routing to 172.16.1.5, router R1 needs to send an ARP request for this specific IP address. For .7, it will have to send another ARP request because these entries are not in the ARP cache table. Whereas when you are using a next hop IP address, as we did in the previous example, 10.1.1.2, each IP address on the 172.16.1.0/24 has a next hop of 10.1.1.2. That's one ARP entry. The recommendation is to avoid using outbound interfaces on Ethernet links. This will be a lot more efficient and saves you resources on your router. Now let's look at the Proxy ARP. In the earlier example, when router 1 wanted to send a frame to 3.3.3.3, it sends an ARP request to R2. R2 does not have the MAC address for 3.3.3.3, yet it has responded with a MAC address. And the MAC address that we see here, 5254.000B3721, is essentially router R2 gigabit 00 MAC address. The reason this is happening is because Proxy ARP is enabled by default. And the way Proxy ARP works is router R2 will respond to ARP request if it has a route for a given subnet. So in this case, R2 did have a route for 3.3.3.3. Proxy ARP is enabled on gigabit 00 on R2, and therefore R2 was able to respond to R1's ARP request with its own MAC address, or the MAC address of its interface gigabit 0/0. What happens if I remove the Proxy ARP? So going into router R2, I just configure no RP Proxy ARP. R1 no longer receives replies when ARPing for 3.3.3.3, and you can see the ARP entry is incomplete, and as a result 3.3.3.3 will be unreachable. And finally, on this last section we will look at IPv6 static routing. So here I go to R2 and I configure an IPv6 address under interface loopback 0. I'm configuring a global unicast IP address, and I'm assigning or I'm using a /128 for host IPv6 address. And then on gigabit 00, I enable IPv6. And the reason for that is so gigabit 0/0 on R2 gets a link local IP address. I run my show IP interface brief on R2, and I can see that gigabit 00 has indeed a link local IP address. I recognize that because it's starting with FE80. And I can see my global unicast IP address as configured for loopback 0. An interesting thing to note here is that the link local IP address on gigabit 0/0 is the same as the one under loopback 0. Now this will give me a little challenge. When I come to configuring my static route on router R1 and I use the next hop IPv6 address for the link local of gigabit 00, where will the traffic go? Will it go to gigabit 0/0 or loopback 0? So this is a problem specific to when using static routes with next hop being a link local IP address. So we will see how this can be tackled. So jumping to R1, I enable IPv6 under gigabit 00, and then I create my IPv6 route. So I started by using the same principle I have used for IPv4, which is IPv6 route, and then use my next hop IPv6 address, which is the address of my loopback 0 on R2, and then I simply added my next hop, that is gigabit 0/0 link local address, which also happens to be the link local IP address of loopback 0. So in this case, I straight away see the error message. The interface has to be specified for link local next hop. So this is the challenge that I mentioned just a few seconds before. So to circumvent this issue, you have to specify your outbound interface when configuring your static route. So going back to R1, I reconfigure my static route, my IPv6 static route, and here I'm using IPv6 route, loopback 0's IPv6, which is my destination. The subnet /128, and then my gigabit interface 00, which is my outbound interface on router 1. And in addition to that, now I can add my link local IP address as a next hop. I test my ping to the IPv6 address configured under loopback 0, and I can see that my ping is successful. One important thing to note is that if your IPv6 route or IPv6 static route is pointing to a global unicast IP address, there is no need to specify the outbound interface. So the outbound interface is only required if your next hop is a link local IP address. We come to the end of this lesson. I hope you have enjoyed it. If you have any questions or comments, as usual, dump them in the section below. If you have enjoyed this content, consider subscribing for more and hit that like button. Once again, thank you for watching.